Alright, I'm officially on to Chapter 4 in Fire in California's Ecosystems, and so far I've been learning about combustion and heat transfer in wildland fuels. But it really reminded me of something that happened the other day. About 3 weeks ago I did a bonfire at the beach with some friends, and we usually do bring some logs there, but to get the fire started, it's better to have maybe some leaves and twigs. And luckily there's some eucalyptus trees right by the parking lot by the beach. So I usually just go into those eucalyptus trees after we park and just grab some leaves and some twigs that we use to start the fire. Now, unfortunately, it had been very foggy the previous 3 days, so I could feel it in these twigs when I was grabbing them that they were maybe too moist. And then when we were starting the fire, there was a large amount of smoke. It was kind of a thick black smoke, and it was kind of windy out too, so it was blowing in people's faces, and it wasn't exactly enjoyable. So I remembered this and hopefully learned my lesson. So then about a week ago, we were doing another bonfire at the beach, and this time I thought, all right, instead of getting the leaves and twigs from like right next to the beach where there's the densest fog, and we had all that smoke, maybe the leaves and twigs under the eucalyptus trees near my house, which is farther inland, won't be as moist, so it'll have a kind of cleaner burn. And good thing, that was exactly what ended up happening, but I finally just learned why that is the case. So I intuitively knew that drier wood would lead to a cleaner burn, but now I've actually maybe figured out the answer. So it all has to do with combustion. So to start there, I think the best place to start is maybe in a much wider view, which is why is wildfire even bad in California? And I often blame that on the Mediterranean climate, which means we have wet winters, dry summers. So at the hottest time of the year, it's also the driest time of the year. Not a big surprise why you'd have wildfires with those conditions, because it could be 80 degrees and then you have 13% relative humidity, your fuels get dry, fire starts, and then it starts going, and then you have afternoon winds as well. But there was something else going on there that I never really thought about, and it was decomposition. So apparently decomposition, or decomposers that engage in that decomposition process, I'm going to be saying a lot of new vocab words today, so hopefully I'm using them correctly in sentences. Apparently decomposers like it when it's warm and moist out. Think of like tropical rainforest and all that decaying leaf litter that you have there. But in California, when it's moist enough for decomposers, it's too cold, so that's winter. And then during summer, when it's hot enough for your decomposers, it's too dry. So there's not kind of preferable conditions or a preferable environment for decomposition to take place. So what ends up happening is we have a lot of dead material building up in California, and this fuel accumulates. Now, it has to get destroyed somehow, or I shouldn't exactly say destroyed, I could say transformed somehow. So the way that this happens oftentimes in California is through combustion. And what's interesting, and something I also didn't know, is that you can think of combustion as the opposite of photosynthesis. So that's why I kind of changed my wording right there to say transformed. And this whole thing kind of reminds me of Star Wars. I believe that's kind of the mythology in Star Wars, that kind of all the elements and atoms in the universe are just transformed into one another through the Force. Well, it kind of seems like that's what's going on with plants and with fire. And with plants, you have photosynthesis, where it's taking carbon dioxide, water, and energy, and it's converting that into oxygen and some kind of organic material, or maybe you could call them hydrocarbons. So I maybe said that too slowly. I might have lost you there. So it's basically CO2 and water. We know plants take out CO2, and they require energy, the sunlight. You always hear about that with photosynthesis. And then it creates oxygen. Think about how we think of plants as breathing in CO2 and breathing out oxygen. And then it also creates that organic material or the plant itself, like its leaves. So that's photosynthesis. Combustion is an oxidation process that is the opposite of that. So in combustion, you can almost just reverse the equation. You're going to have your hydrocarbons or your organic material. You're going to have your oxygen. Remember, fires need oxygen in order to burn. And then that's going to be turned into water, CO2, and then the most important one in terms of fire, I would say, is energy. So I named two things there. So you have your organic material and your oxygen, but there's one more that's important to complete what you'd call the fire triangle, and that is heat. So I might have confused you a little bit right there because there's technically two fire triangles in Wildfire. Apparently there are other shapes that we can use, but there's the fire behavior triangle, which is the three keys to fire behavior. That's fuel, weather, and topography. And then there's just the fire triangle, which is heat, oxygen, and fuel. And these are the three things that you need in order for a fire to happen. And I guess it doesn't have to be just wildfire that you're talking about, but that is the setting that we're using this terminology in. So the big thing about this is these are the three keys to fire: heat, oxygen, fuel. So if you want to stop fire, you're going to have to break the link between those, or maybe eliminate one of the sides of the triangle. So that's either going to be reducing your heat, reducing your oxygen, or reducing the heat. Oh, I said heat twice. Heat, oxygen, and fuel. So got in my own head there a little bit. So perfect example, reducing the oxygen. I think that's like when wildland firefighters are throwing dirt on the fire. That's maybe just covering up the fire. Reducing the heat, spraying some water on it. Reducing the fuel, that's like when you see them with, what are the tools called? Maybe a Pulaski or a McLeod? I forget which one's which. But when they're scraping all the grasses and making that little fuel break, in each of those cases, they're trying to take out one of the sides of the fire triangle so that fire no longer occurs. So let's say fire does occur. Combustion is going to take place in three different phases. It's going to be first your preheating phase, then your gaseous phase, and then your smoldering phase. Now the preheating phase, I think this one's pretty interesting. It's made up of two things. It's hydration and pyrolysis. And I know I've just thrown out a lot of different scientific words here. So again, what we're talking about is within a fire, and a fire is moving forward, you're going to have preheating, you're going to have gaseous, and smoldering, and those are your three phases of combustion. So in preheating, you have hydration. That's a fancy way of saying water evaporating out of your fuels. So first, the water has to reach its boiling temperature, then it has to evaporate, and then that water vapor has to reach the temperature of the flames. And that takes a lot of energy from the fire to be able to do that. So the reason that's important is because if there's too much moisture in your fuels, then your fire is not going to have enough energy to even catch that fuel on fire because it has to evaporate the moisture out of that fuel first. And I forget the exact term of what you would call it if there's too much moisture in the fuel for it to catch on fire. I think it's called some sort of threshold. It's like the moisture of extinction, something like that. So that's part of the preheating, evaporating the moisture out of your fuels. And then you also have, so that's hydration, and then you also have pyrolysis. Now this one took me a little while to understand, but it sounds like it's basically heating up the fuel itself until the gases within that fuel, what you'd say is volatilize, or they become volatile. Hopefully using those words correctly. So it's increasing the temperature of the gases in the fuel as well until it reaches their ignition point. And then at this point is when you reach into the gaseous phase. Now this is something I think I'd learned in the past, but I kind of forgot about. But on a fire, I've never really thought about what is the actual flame that you're looking at. but it's gases that are combusting. So that's the gases that were in your fuel that reach their ignition temperature, and now there's a flame. So that's going to be when you have a lot of heat energy being produced. But typically on a wildland fire, it's not going to be complete combustion. It's going to be what you call incomplete combustion. So that's where you have maybe some liquid droplets, some solid droplets that are maybe just floating above the fire. It's what we'd call smoke. And because it's not complete, not all of that material is turned into the energy in that combustion equation that we were talking about earlier. So this is something that reminded me of that campfire that I was talking about earlier, where I had very incomplete combustion because there was so much moisture in the fuels that a lot of the heat energy from the fire was being used to evaporate the moisture instead of just kind of combusting the gases and just leading to a full-on flame and then burning out the wood as well. So gaseous phase is going to be more difficult to get into if you have a lot of moisture in your fuels, because that's going to just take some of the energy from the fire and basically waste it on evaporating out the water. That's why it's so important how dry your fuels are, whether California is in a drought or not, whether we picked up a lot of rainfall last winter or we didn't. So that's the gaseous phase, when your gases become volatile and, what was the exact word they used? Vaporize. Pretty cool vocab word right there. And then the final phase is going to be smoldering. So this is maybe after your flaming front has gone through. And instead of the gases being on fire now, it's the surface of the fuel itself. And then that's kind of what you'd call charcoal. And everyone knows what smoldering looks like. And in some cases that can go on for months at a time. It can even go on through an entire winter. You can have smoldering like within a branch or even within the soils. And then the next summer it gets hot again, and then all of a sudden you have all these fires popping up. And it was because of smoldering that had continued throughout the entire year. I remember this happened on the CZU lightning complex, where an entire year later, it was a really hot day, and then all of a sudden we started seeing all these fires popping up, and they figured out it was smoldering that had been left over from the fire that happened a year before. So those are your 3 phases of combustion. And there's one more little framework we can talk about that relates to all of this, which is your 3 forms of heat transfer. Because a lot of what we've been talking about is heat transfer and energy, and also just transfer between matter. But 3 forms of heat transfer, you probably already know them. It's conduction, convection, and radiation. So conduction, that's heat passing through a solid from molecule to molecule. So that's like when you grab your hot metal pan and you burn your hand. That's the conduction going through that metal pan. And on a fire, I don't imagine this has huge impacts. It'd be like if the surface of your log started heating up and then that heat started going into the middle of the log, or maybe heat going through your soils. Where I'd say there's going to be bigger impacts on a wildfire are going to be with convection and radiation. So with convection, that's heat going through a liquid or a gas. So you could think about if you put your hand above a fire and your hand gets very hot, that's because the air above the fire is heating up and the air is rising, and then that's heating up your hand. That's convection. Or you can kind of think about it like when you're boiling water, how it's all kind of moving around, or in a lake when you have like some warm spots and some cold spots and it's all moving around. That's all convection, different forms of it. And then radiation, that's going to be like if you're standing on the side of your fire and you feel that heat radiating on you. So then the natural example of this would be like the sunlight radiates from the sun and heats up the earth. It's through, I think it's called electromagnetic waves, is how you have radiation. And that can go through transparent solids, liquid gases, even vacuums, like when it goes through space. And then one interesting thing about radiation is it's inversely proportional to the square of the distance. Hopefully said that right. But what it means is if you get if you go half the distance to the fire, so you cut your distance to the fire in half, you're going to be picking up 4 times as much heat energy. So it's inversely proportional to the square of the distance. Just thought that was kind of interesting. What's most important about these, though, is with convection and radiation, both of those are going to be able to preheat your fuels before the fire gets there. So we're tying that back into your combustion. So you're able to kind of kickstart the combustion process through convection and radiation. So you have your flames, maybe they're on a hill, maybe the flames are tilting uphill, and the flames through radiation are heating some of the plants up. It's evaporating some of the water out of the plants, it's getting the gases within those plants close to their ignition temperature, or it's getting the plant itself close to its ignition temperature. And then you also will have maybe your wind blowing uphill. So that's also taking some of the heat and it's pushing some of that hot air up the hill through convection. And then once again, that's also engaging in your preheating, which is evaporating the moisture out of the fuels and raising the temperature of the fuel as well, getting it closer to that gaseous stage. So why that's important is because by the time the flame gets there, those plants are just going to be ready to combust, or maybe they will. But they'll be a lot more ready than if it was a flat surface and all the heat was just going straight up into space and you had your plants maybe getting some of that radiation but missing out on the convection. So then by the time the flame got there, those plants weren't ready to combust. Some of the energy from the flame had to be wasted to evaporate out the water, and then it's slowly moving versus that fire going uphill where it has heat transfer through convection, radiation, leading to that preheating, evaporating the moisture, and then the fuels easily catch on fire. So I just kind of liked how the whole beginning of this chapter 4 all ties perfectly together. I'm interested to read the rest of this chapter. When I first looked at it, I thought, oh, this one might be a bit complicated. It looks like they're getting into chemistry and some pretty detailed stuff. But so far, I'd say it's been one of my favorite sections that I've read, so I can't wait to read more. If you want to learn more about wildfire as well, you can stay tuned, and thanks for watching.